Let's break down how AI on your laptop actually works and what's about to change this year. Here's you in your laptop. Today, when you ask AI for something, the request doesn't stay on your machine. It races over the internet to a data center, maybe hundreds of miles away. The data center does the thinking, then sends the answer all the way back. That's cloud AI, and it quietly costs you in 3 ways. 1. It only works when you have Wi-Fi. 2. It usually needs a monthly subscription. And 3. Your private data has to leave your device. Now, here's what changes this fall. Same question. But the new laptops pack a powerful AI chip with 128 gigabytes of memory right inside. That's big enough to run a serious AI model on the laptop itself. No data center, no round trip, no internet required. And that flips 4 things in your favor. It works offline, there's no subscription, your data stays private, and the answers come back instantly. So that's the real shift. You stop renting AI in the cloud and start owning it on your own machine. So before you buy a laptop this year, ask one question. Can it run the AI with the Wi-Fi off? Tech explained in one clear picture. I'll see you in the next one. Last time, we said a new laptop can run a giant AI model with the Wi-Fi off. But hang on, these models are huge. So how does one actually fit on your laptop? The trick is something called quantization. First, what even is an AI model? Strip away the magic, and it's just a giant pile of numbers. Each number is a parameter, a tiny dial the AI tuned while it was learning. A model can have billions of them. That's all 7B or 70B means. 7 billion or 70 billion parameters. More dials usually means a smarter model, but a bigger one. Here's the catch. Every one of those numbers has to be stored in memory. Normally, each parameter takes 16 bits, about 2 bytes. Do the math. A 7 billion parameter model needs roughly 14 gigabytes. A 70B model? Around 140. That 140 gigabytes won't fit on a normal laptop. This is the wall. So here's the trick, quantization. It just means storing each number with less precision. Take a parameter like 0.7349. Do you really need all those digits? Round it to 0.7. Shrink each one from 16 bits down to 4 bits, and the whole model gets about 4 times smaller. Now, that 7B model is roughly 4 gigabytes, and the 70B drops to about 35. Suddenly, it fits easily on a 128 gigabytes laptop. Is there a cost? A little. It's like saving a photo as a JPEG. You trade a tiny bit of detail for a ton of space. But modern 4-bit models are so good, the difference is usually hard to notice. And this is why it matters to you. Next time you open a Llama or LLM Studio and see a model tag 7B, Q4, you'll know exactly what you're looking at. It's a dial, smaller and faster, or bigger and smarter. You're choosing how much AI your laptop can hold. That's the trick that puts a private AI in your hands. I'll see you in the next one. We've said an AI model is a giant pile of numbers. But what do those numbers actually do? Here's the surprising truth. A chatbot like ChatGPT is really just predicting the next word. Let me show you. It starts with your prompt. Say you type, "The cat sat on the..." First, the text is broken into tokens, little chunks, roughly words or pieces of words. But a computer can't read words. So each token becomes numbers, a list that captures its meaning. Those numbers flow into the model, that giant pile of parameters from last time. Inside, it does one clever thing. It looks back at all your words and decides which ones matter most for what comes next. That's called attention. And here's the whole job. It outputs a probability for every possible next word. For the cat sat on the, it might say, mat, 71%, floor, 12%, roof, 3%, and so on. It picks one, usually the top, and that's the next word, mat. Then the trick, it adds that word back to your text and runs the whole thing again. One word at a time. That's literally why ChatGPT types out its answer in front of you. So why does this matter to you? 1. The AI doesn't know facts. It predicts what sounds right. That's why it can be confident and flat out wrong. We call that a hallucination. 2. It only has your words to go on. A clearer prompt literally changes the prediction. That's why prompting works. 3. There's a dial called temperature. Low gives safe, predictable words. High gives more creative, surprising ones. That's it. No magic, no thinking, just the world's best next word guesser, running over and over. Now you know what's really happening every time you hit send. I'll see you in the next one. Last time we learned an AI only knows what it was trained on, so it can't read your files and it'll happily make things up. So how do tools that chat with your documents actually work? A trick called RAG. Let me show you. The problem, a model's knowledge is frozen at training. It's never seen your notes, your company docs, or today's news. RAG's fix, before answering, let the AI look things up in your documents. Step 1. Index them once. Split each document into small chunks, about a paragraph each. Turn each chunk into an embedding, numbers that capture its meaning. Store them all in a vector database, a library organized by meaning, not keywords. Step 2. You ask a question. It becomes a vector too. The database instantly finds the chunks closest in meaning to your question. That's the retrieval in RAG. Those chunks get pasted into the prompt, right next to your question. Now the model answers, using that real, retrieved text, not just its memory. And since it's quoting your documents, it can even cite its sources. So why does this matter to you? 1. The AI can finally answer about your stuff, a PDF, your notes, a whole company wiki. 2. It stays current. Drop in a new document and it knows it instantly. No costly retraining. 3. Far fewer hallucinations, grounded in real text, and it can show where it got the answer. That's RAG. Don't make the model memorize everything. Just hand it the right page at the right moment. Now you know what's really happening when you chat with your documents. I'll see you in the next one. Last time we learned an LLM just predicts text. It can talk, but it can't do anything. So how do AIs that book flights, search the web, or write and run code actually work? They're agents. Let me show you. A normal chatbot is a brain in a jar. Ask it for today's weather and it can only guess. No hands, no internet, no way to act. An AI agent fixes that with 3 things: a goal, tools, and a loop. It starts with a goal you give it. Say, find me the cheapest flight to Tokyo. The LLM is the brain. Its job now isn't to answer, it's to decide the next step. So it picks a tool. Agents come with tools: web search, a code runner, APIs, your files. It uses one, say, search flights, and the tool runs for real. The tool returns a result, and the agent reads it. This is the observation. Then the key part, it loops. The result goes back to the brain, which decides the next move. It keeps going, search, compare, check dates, until the goal is actually done. And only then does it give you the final answer, or take the final action. So why does this matter to you? 1. AI stops just talking and starts doing, booking, buying, researching, automating real tasks. 2. This is what's under the hood of coding assistants that edit your files and research agents that browse for you. 3. More autonomy means more risk. A good agent asks for your approval before doing anything big. That's an agent, not a smarter chatbot, but an LLM with hands and a to-do loop. Now you know what people really mean by AI agents. I'll see you in the next one. Ever notice ChatGPT forgetting what you told it earlier in a long chat? It's not being lazy, it literally can't see it anymore. The reason is the context window. Let me show you. Quick recap. An AI works by reading text and predicting what comes next. But here's what people miss. The AI has no memory. None. Every single reply, it rereads your entire conversation from scratch. That chunk of text it can see right now, that's the context window. It's measured in tokens, word pieces, about 3/4 of a word each. And the window has a fixed maximum size. As your chat grows, it fills up. Your messages, the AI's replies, all of it. Then, the catch. When a conversation gets longer than the window, the oldest text falls off the end. The AI can't see it, so it forgets. It's not forgetting like a person. That text is simply gone from its view. So why does this matter to you? 1. In a long chat, it forgets the start. So don't be surprised when it loses the thread. 2. For a new topic, start a fresh chat. A clean window means sharper answers. 3. Keep the important stuff in your latest message. That's what it's guaranteed to see. And remember RAG? That's one fix. Fetch just the relevant bit instead of stuffing everything in. So that's the context window, the AI's short-term memory. Once it's full, the oldest stuff slips away. See you next time. Same AI, same question, but 2 wildly different answers. The only difference? The prompt. Here's how to get dramatically better results from any AI. Remember, an AI just predicts text from what you give it. So your prompt steers everything. Here's a weak prompt. Write about dogs. Vegan. Vague out, a generic, unfocused wall of text. Now, let's engineer it with 4 simple ingredients. 1. A role. Act as a vet. 2. Context. I have an 8-week-old puppy, first week home. 3. The task. List the 3 things to focus on. 4. A format. As a short, friendly bulleted list. And now the answer is specific, useful, and exactly what you needed. Same model. Night and day difference. You're steering the prediction. So here are your levers. Be specific. Swap vague words for exact ones. Get a role and context. Tell it who to be and what you're working with. Ask for a format. And show an example if you can. Bullets, a table, steps, a tone. A prompt isn't a search box. It's a brief. Who, what, and how. I'll see you in the next one. An AI just told you a fact with total confidence, and it was completely wrong. That's a hallucination. Why does it happen? Let me show you. Recall. An AI predicts the word that sounds right, not the one that is right. It has no fact checker and no database inside. It's pure pattern completion. So when it hits something it doesn't actually know, it doesn't stop. It invents the most plausible sounding answer, like a citation that doesn't exist. That's a hallucination. Confident, fluent, and wrong. And it sounds exactly as sure as when it's right. Confidence is not correctness. So why does it happen? 3 big reasons. Gaps, or outdated training data. A vague prompt it's forced to guess at. And it's built to always produce an answer. So how do you protect yourself? Ground it. Use RAG, or paste in the source text. Ask for its sources, and tell it that I don't know is a perfectly fine answer. And verify anything that actually matters. Treat AI like a confident intern. Brilliant first drafts, but always check the facts. See you next time. How does an AI know that dog and puppy are related, but dog and car aren't? They don't share a single letter. The answer is embeddings. Back in the RAG video, we turned text into numbers called embeddings. Here's what that actually means. An embedding turns a word, or a whole sentence, into a point in space. And here's the magic. Things with similar meaning land close together. So dog, puppy, and cat cluster over here in the animal region, while car and truck sit way over there with the vehicles. Dog and puppy are neighbors, even with no letters in common. It's meaning, not spelling. There's even structure to it. The direction from king to queen is the same as man to woman. And this is how search by meaning works. Find the points closest to what you asked. Ask for a young dog, and the nearest points are puppy and dog. No keyword match needed. So why does this matter to you? It's search that finally gets your intent, not just your keywords. And it's the quiet engine behind RAG, recommendations, and find similar everywhere. It even works across languages and across images and audio too. Embeddings are a map of meaning. Close means similar. See you in the next one. There are 2 ways to make an AI truly yours, fine-tuning and RAG. And people constantly pick the wrong one. Here's how to choose. Say you want an AI that knows your world. 2 very different tools. First, fine-tuning. Think of it as sending the model to school. It retrains the model itself, its weights, so it learns how to respond. It's best for a consistent style, tone, format, or a specialized skill. But it's slow, costs money to train, and you have to redo it whenever your information changes. Now, RAG. Think of it as giving the model an open book, your documents. It looks them up at answer time, changing what the model knows without touching the model. It's best for facts, your private docs, and anything that changes. And you can update it instantly, cite sources, and keep it cheap to run. So which should you use? Need fresh or private facts? Reach for RAG. Need a consistent style or skill? Finitune. And honestly, most real products use both. Fine-tuning teaches it how to talk. RAG gives it what to know. See you next time. You can run AI 2 ways, in the cloud or on your own machine. Which one is right for you? Let's compare. Cloud AI, like ChatGPT, Claude, or Gemini, runs on giant company servers. The upside, the most powerful models, nothing to set up, and it works on any device. The downside, it needs internet, usually a subscription, and your data leaves your device. Local AI, with tools like Ollama or LM Studio, runs right on your computer. The upside, it's totally private, works offline, free after your hardware, and has no usage limits. The downside, you need a capable machine, the models are smaller, and you manage it yourself. So which should you use? Want privacy? Offline access or heavy daily use? Go local. Want maximum power? Zero setup on any device? Go cloud. And many people do both. Sensitive work local, heavy lifting in the cloud. Cloud is power and convenience. Local is privacy and control. Pick per task. See you next time. We've seen that a chatbot is really just predicting the next word. But that raises a bigger question. How do you turn a pile of numbers into something that can actually answer you? A modern chat model is built in 3 stages. Let me walk you through them. Stage 1 is pre-training. You take a huge chunk of the internet, books, websites, code, and you train the model to do one thing: predict the next word over and over billions of times. Out of that comes raw general knowledge and a feel for language. But there's a catch. The model only knows what was in that data. That snapshot in time is exactly why every model has a knowledge cutoff. At this point, the model is smart but unruly. Ask it a question, and it might just continue the text instead of answering because no one has taught it what a good answer even looks like. So stage 2 is fine-tuning, also called instruction tuning. Here you show the model thousands of example pairs, a question and a good, helpful answer written by people. By copying those examples, the model learns to follow instructions to actually respond when you ask it something instead of just rambling on. But following instructions isn't enough. Of 2 correct answers, which one is clearer, kinder, or safer? For that, we need stage 3. Stage 3 is RLHF, reinforcement learning from human feedback. It works like this. The model writes several answers, and humans rank them from best to worst. Those rankings train a second model, called a reward model, that learns to score any answer the way a person would. Then the main model is polished against that reward, nudged again and again toward being helpful, honest, and safe. That polishing step is what people mean by alignment. So why does all this matter to you? 1. The knowledge cutoff is real. Out of the box, the model doesn't know recent events. It only knows its training snapshot. That's why connecting it to tools or search matters. 2. That friendly, helpful assistant personality isn't innate. It was trained in deliberately during fine-tuning and RLHF. 3. The model learns from human data, so any biases in that data can get baked in. Better data and better feedback are how you push back on that. 3 stages: pre-train for knowledge, fine-tune to follow, RLHF to align. That's how a raw model becomes the assistant you talk to. I'll see you in the next one. You type a few words, and a tool like DALL-E, Midjourney, or Stable Diffusion paints a brand new picture. So how does it actually do that? The answer is wonderfully strange. It starts with pure noise. Here's the surprising part. The model doesn't start from a blank canvas. It starts from a screen of random static, like an old TV with no signal. Just meaningless dots. But it doesn't get there alone. First, your text prompt gets turned into numbers, an embedding that captures what you actually asked for. That embedding becomes the guide. At every step, it steers the picture toward your words, like a compass pointing the way. Now the real trick. The model looks at the noise and removes just a little bit of it, guided by your prompt. Then it does it again and again, dozens of small steps, each one a touch clearer than the last. Slowly, shapes appear out of the static. Then colors. Then details. An image emerges that matches what you described. So how did it learn this? In training, it watched millions of real images get slowly buried in noise, step by step. Then it learned to run that backwards, to predict and remove the noise. Reverse the process enough times, and you can build an image from nothing but static. So why does this matter to you? 1. Your exact wording steers every single step. Change a word, and you nudge the whole path. That's why prompt wording matters so much. 2. It is not a collage. It's not pasting together bits of existing photos. Every pixel is generated fresh from noise. 3. Fine details are hard. Hands, fingers, and tiny text often come out wrong because they're complex and easy to smear during denoising. And one more. 2 runs almost never match. The starting noise, called the seed, is random, so the same prompt can give very different pictures. That's diffusion. It doesn't find your image, it sculpts it out of pure randomness, one small step at a time. You've probably noticed some AI models now say they're thinking before they answer. So what's actually going on, and is it just a gimmick? Let's break it down. Start with a normal language model, the kind behind most chatbots. You ask a question, and it answers almost instantly. Under the hood, it predicts its reply one word at a time, racing straight to the answer. Fast, but with no real workspace to think in. That's fine for easy stuff. But on a tricky multi-step problem, like a logic puzzle or hard math, it often blurts out a confident answer that's just wrong. Now, meet the reasoning model. Think of O1 style or thinking models. Same question goes in, but watch what happens next. Before answering, it generates a hidden chain of thought. It writes out its own reasoning, step 1, step 2, step 3, working through the problem. This scratch work is usually hidden. You don't see it, but the model is genuinely reasoning through the steps, the way you'd work a problem on paper. It can even catch its own mistakes midway, backtrack, and try a different path before it commits. Only then does it give you a final, checked answer. And on hard problems, it's far more likely to be right. The catch, all that thinking is extra work. Those hidden steps are called thinking tokens, and the model burns time and compute generating them. So it's a trade. You spend more time and more money, and in return you get much higher accuracy on genuinely hard problems. So why does this matter to you? First, reasoning models are far better at hard math, logic, and coding. If a problem has real steps, they shine. Second, they're slower and cost more, and you're paying for that hidden thinking even though you never see it. Third, match the tool to the job. Use a reasoning model for genuinely hard problems and a fast model for quick lookups and simple chat. Bottom line, a normal model answers fast, a reasoning model thinks first. Knowing which to reach for saves you time, money, and wrong answers. How did one chip company suddenly become worth more than almost any other on Earth? The answer is hiding in how AI does its math. Under the hood, AI is mostly one kind of work. Billions of simple operations on big grids of numbers, matrix multiplications. And the magic is, most of those tiny operations don't depend on each other. They can all happen at the same time, in parallel. Now, meet the two chips. On the left, the CPU, the brain of a normal computer. The CPU is just a few cores, but each one is big, fast, and very smart. Great for doing complicated tasks one after another, in sequence. That's perfect for running your operating system or a web browser, where each step often depends on the last. On the right, the GPU originally built to draw video game graphics, painting millions of pixels at once. Instead of a few big cores, a GPU has thousands of small, simple cores, all working side by side. Each core is weaker than a CPU core, but there's so many of them that together they crunch thousands of operations at the very same time. See the match? AI is mostly parallel math. A GPU is mostly parallel cores. It's the perfect fit. So training and running AI lean heavily on GPUs. And that's why Nvidia exploded. They make the GPUs nearly every big AI system runs on, which turned them into one of the most valuable companies on the planet. So why does this matter to you? 1. It's why AI is expensive and energy hungry. Thousands of cores running flat out burn a lot of electricity, and those bills get passed on to you. 2. If you want to run AI on your own machine, you need a decent GPU with plenty of memory, which is exactly why we use smaller, quantized models locally. 3. It's the heart of the global chip race. Countries and companies are fighting over who can make and buy these AI chips, because compute is now power. So the whole story is simple. AI is parallel math. GPUs are parallel machines. And that match is why your phone, your power bill, and world politics all now run through one little chip. Last time we saw that AI agents need tools. Search the web, read your files, call your apps. But there's a messy problem hiding behind that. Let's talk about MCP. Here's the issue. To let an AI use a tool, someone has to write custom code connecting them, a little piece of glue. But you don't have one AI and one tool. You have many AI apps and many tools, your files, GitHub, Slack, a database. So every app needs its own custom connector for every tool. The result is a tangled mess of one-off code that nobody wants to maintain. This is where MCP comes in, the Model Context Protocol. Think of it like USB-C, but for AI tools. One open standard, one shared plug, instead of a different cable for everything. Now the AI app talks to one universal connector, and that connector talks to all your tools in the same standard way. So how does it actually work? First, the AI asks the connector a simple question. What tools do you have? The connector answers with a menu, search files, send a message, query the database, each with a clear description. Then the AI calls the tool it needs in a standard format. This idea is called function calling. MCP is what makes it work the same way across every app. The big win: build a tool once, and any MCP-compatible AI can use it. No more rewriting glue for every combination. So why does this matter to you? 1. It's why your AI assistant can suddenly use your real apps and files, not just chat about them. 2. It created a fast-growing ecosystem. Like app stores, there are now plug-in tools for almost anything. 3. You stay in control. You decide which tools and data an AI is allowed to touch, which matters for your security. That's MCP, one standard plug that lets any AI safely connect to the tools you already use. We've seen that embeddings turn text into points in a map of meaning, and that RAG uses them to find the right page. But where do all those points actually live? That's the job of a vector database. Quick recap: an embedding turns text, or even an image, into a vector, a list of numbers that's really just a point in meaning space. Similar things land close together. Now imagine you don't have 3 points, you have millions of them, one for every chunk of every document you own. You need somewhere to keep them. That's a vector database. It stores millions of these vectors, and it's built to answer one question incredibly fast. That question is, which store vectors are nearest to this new one? It's called nearest neighbor search or similarity search. Here's the key difference. A normal database matches exact values or keywords. Search for cat, and it finds the literal word cat. A vector database matches by meaning. Search for cat. It can also surface kitten, feline, or even a photo of one, because their vectors sit nearby. So the flow is simple. Your documents become embeddings, and those vectors get stored in the database, indexed by meaning. Later, a query comes in. It gets turned into a vector too, using the same embedding model. The database runs a nearest neighbor search and hands back the top matches, the closest points to your query. But here's the catch. With millions of vectors, comparing your query to every single one by one, will be far too slow. So vector databases use smart indexes, like one called HNS, that jump straight to the right neighborhood. They don't check everything, so they stay fast even over millions of items. So why does this matter to you? 1. It's the engine under RAG and semantic search. It's how an AI app searches your knowledge by meaning, not just keywords. 2. It powers find similar and recommendations. Similar products, similar songs, similar images, all just nearby points. 3. It does all of this at scale, returning the closest matches from millions of items in milliseconds. So that's a vector database, a giant map of meaning built to instantly find what's nearest. The quiet engine behind modern AI search. I'll see you in the next one. Every AI app you use, from chatbots to writing tools, talks to the AI behind the scenes using something called an API. So what actually is one? Let me make it simple. API stands for Application Programming Interface. In plain English, it's just a defined way for one program to ask another program for something. The classic way to picture it: a restaurant. You sit down and look at the menu. That's the list of things you're allowed to order. You tell the waiter what you want. The waiter is the messenger that carries your order back and forth. The waiter takes it to the kitchen, where the food actually gets made. The kitchen is the server, the program doing the real work. A few minutes later, the waiter brings back your dish. That's the response, exactly what you asked for, delivered to your table. And here's the beautiful part. You never have to know how the kitchen works. You just order from a menu and get your food. Now let's swap in AI. Instead of a person, it's your app that wants something from the AI. Your app sends a request. Your prompt, the question or task, plus an API key, a secret password that tells the provider who you are. That request travels over the internet to the AI provider's API, the server that runs the model and does the thinking. The AI processes it and sends back the response, the answer, and the whole round trip usually takes just seconds. So why does this matter to you? First, this is how every AI app is built. Tools call the OpenAI or Anthropic APIs in the background. You just see the friendly interface on top. Second, your API key is secret like a credit card. Anyone who gets it can spend on your account, so never paste it into public code. Third, you usually pay per usage, measured in tokens, and there are rate limits that cap how many requests you can send per minute. So an API is just a menu and a waiter for software. Your app orders, the AI server delivers, and you never touch the kitchen. Now you know what's really happening every time an app talks to AI. Last time, we saw a single AI agent, a brain with tools and a loop, working through a task on its own. But what happens when the job is too big for one? For large, multi-step goals, you don't use one agent. You use many specialized agents that work together like a team. A common pattern starts with a manager, sometimes called an orchestrator. The manager takes your big goal and breaks it into parts, then hands each part to a specialist that's focused on just that job. First, a researcher. Its job is to go find the facts and gather what's needed. Next, a coder. It takes those findings and actually builds the thing, the code, the draft, the result. Then a reviewer. Its only job is to check the work for mistakes. And here's the key idea. They pass results to each other. The researcher's findings flow to the coder. The reviewer checks the coder's work. If something's wrong, it sends it back to be fixed, and they try again. That loop repeats until the work passes the check, and a manager returns one finished result. So why does this matter to you? 1. A team can handle far bigger, multi-step jobs than a single agent ever could on its own. 2. Because each agent specializes and they check each other's work, the quality of the result goes up. 3. But it costs more. Every agent is more AI calls, more money, and more moving parts to manage. This is where the whole field is heading. AI workforces, teams of agents that take on real projects together. A single agent has hands and a to-do loop. A team adds a manager and specialists, so the agents can divide the work and check each other. That's multi-agent AI. Ever told ChatGPT your name, come back the next day, and has no idea who you are? Let's fix that, and let's see what's really happening when an AI claims to remember you. First, the truth. By default, an AI is stateless. It has no memory between chats, and the context window it reads is limited. So when you start a new chat, it forgets everything you ever told it. Now the app's added a memory feature. But here's the twist. It does not give the model real memory. Watch what actually happens. As you chat, the app quietly extracts key facts about you, your name, your preferences, the projects you're working on. It saves those facts to a separate store, a little notebook that lives outside the model. Later, you open a brand new chat. The model itself still remembers nothing, but the app steps in. It retrieves the facts that are relevant to what you just asked, often using the same retrieval or RAG style lookup we covered before. Then it injects those facts into the context window right alongside your message before the model ever sees it. So when the model answers, it looks like it remembers you. Really, the app just refed your notes. That's the whole trick. Memory is notes the app keeps about you and quietly slips back into the prompt, not the model truly remembering. So why does this matter to you? 1. You get personalized answers without re-explaining yourself every single time. It already knows your context. 2. It's storing facts about you, so privacy matters. The good news, you can view, edit, and delete what it's saved. So go check it. 3. You can steer it. Just say remember that and you can tell it exactly what to keep. So next time ChatGPT remembers your name, you'll know the secret. There's no magic memory, just a smart notebook feeding the prompt. This is Tech It Away. You don't need the cloud to run AI. With a free tool like Ollama or LM Studio, you can run open models right on your own laptop, fully private and offline. But which model can your machine actually handle? Let's make it simple. The one thing that decides this is memory. That means your RAM, or if you have one, your graphics card's VRAM. The model has to fit in there to run smoothly. Here's the rule of thumb, and it assumes you grab the 4-bit quantized version of a model, the squeeze-down build we covered before. If you have about 8 gigs of memory, you're in small model territory, roughly a 7 to 8 billion parameter model, which needs about 5 to 6 gigs. That runs on most modern laptops. Around 16 gigs of memory? You can step up to a mid-size model, roughly 13 billion parameters, needing about 10 gigs. Got 32 gigs or more, or a strong GPU. Now the large models open up. A 70 billion parameter model needs about 40 gigs or more. So which models do you actually download? Look for these open families. Names like Llama, Quinn, Gemma, Phi, and Mistral. Each comes in several sizes, so you pick the one that fits your memory. The trade-off is simple. Smaller models are faster but less capable. Bigger ones are smarter but heavier. Pick the biggest that fits comfortably and leave some headroom. So why does this matter to you? 1. It's free, private, and offline. The model runs on hardware you already own, and nothing leaves your device. 2. Match the size to your machine. Pick a model that fits in memory, and it runs smoothly instead of crawling. 3. Quantization is your friend. Those 4-bit versions are what make bigger models fit on normal hardware. One evergreen tip. Models change fast, so check Ollama's library for the current versions and sizes before you download. Match the model to your memory, grab the quantized build, and you've got your own private AI. I'll see you in the next one. Tools like GitHub Copilot, Cursor, and Claude Code can write working code from a plain English request. It feels like magic, but it isn't. Let me show you what's really going on. Under the hood, it's a large language model, an LLM, trained on a huge amount of public code. And here's the key. It predicts code the exact same way a chatbot predicts words, one piece at a time. So if it's just predicting, why is it so good at your project? The real magic is one word. Context. It starts with you. You describe what you want in plain English, like add a button that saves the form. Then the tool quietly gathers context, your open file, the nearby code, and often the wider code base, retrieved by meaning using embeddings, the same idea behind RAG. All of that, your intent plus your code, is fed into the AI model. The model predicts the most likely code that fits and hands you a suggestion or an edit. Then the most important step, you review it and you run it. If it's good, you keep it. And that's the loop. You describe, it sees your context, it writes, you review and run, and around again, tightening the code with each pass. Agentic coding tools go one step further. They can run commands themselves, read the error messages, and fix the code in a loop, the same agent loop we covered before. But you stay in control and review what changes. So why does this matter to you? 1. It's a massive speed up. Boilerplate, repetitive code, and looking up syntax takes seconds, and it's a fantastic way to learn a new language by example. 2. It can still hallucinate code. It can confidently invent a function that doesn't exist. So you must always read and test what it writes. 3. Treat it as a co-pilot, not an autopilot. It's brilliant at the typing, but you bring the judgment. You are still the pilot. So an AI coding assistant isn't a robot programmer. It's a next code predictor supercharged by your context, with you reviewing every move. Now you know what's really happening when the code writes itself. I'll see you in the next one. Every AI model you use falls into one of two camps, closed or open. The difference quietly shapes your cost, your privacy, and how much control you have. Let me make it simple. First, closed models. Think of the big names like GPT, Claude, and Gemini. These are proprietary. You reach them through an API or an app. The actual weights, the brains of the model, stay secret on the provider's servers. The upside, these are usually the most capable models on the planet, and they're the easiest to use. Nothing to install. The catch, you're renting them. You pay ongoing fees, you depend on that one company, and your data leaves your device and goes to them. Now the other camp, open or open weight models. Families like Llama, Mistral, Quinn, and Gemma. Here the weights are downloadable. You can run them yourself, on your own machine or your own server. That means you can use them free, keep your data fully private, and even fine-tune them to your own needs. The trade-off? You handle the hosting and the hardware, and these models are often a step behind the very frontier. So what should you pick? If you want maximum capability with zero setup, a closed model through an API is the easy win. If you care about privacy, cost, or full control, an open model you run yourself is the way to go. And plenty of teams use both. A closed model for the hardest tasks, an open one for sensitive or high-volume work. Why does this matter to you? Because it decides where your data goes, what you pay over time, and how much you truly own what you build. Closed equals top capability and convenience. Open equals control, privacy, and freedom. Now you know which lever you're pulling. Here's a question that breaks even the smartest AI models. How many R's are in the word strawberry? Ask a chatbot, and it'll often say 2. The real answer is 3. So why does a system that can write essays trip over a kid's spelling question? The secret goes back to how an AI reads. Remember, it never sees letters. It only sees tokens. When you type strawberry, the text first hits a tokenizer. The tokenizer chops the word into a few chunks called tokens. Strawberry often splits into something like straw, plus berry. And here's the key part. Each token is just a number to the model. Straw might be token 6128. Berry might be token 4091. So the model never actually sees the letters STRAWBRRY. It only sees two numbers. The individual R's are invisible to it. That's why it struggles to count them. It's like asking you how many R's are in a word you only ever heard out loud, never saw written down. And this one quirk explains a whole family of weird failures. Counting letters, spelling a word backwards, some simple digit math, even making things rhyme. All the tasks that need letter-level detail get strangely hard. So why does this matter to you? One, it's not dumb. The model just perceives text in chunks, not letters. Knowing that tells you when to trust it and when to double-check. Two, it explains a whole class of odd mistakes at once, so they stop feeling random. Three, there's an easy fix. Ask it to spell the word out letter by letter first, or use a newer reasoning model or a tool, and suddenly it counts just fine. So the strawberry problem isn't a sign that AI is broken. It's a window into how it actually sees the world, in tokens, not letters. Now you'll know exactly why it happens and how to work around it. I'll see you in the next one. Here's a strange weakness hiding inside almost every AI assistant. People can hijack it just by leaving it the right note. It's called prompt injection. Let me show you how it works and why it matters. Remember this, to an AI, everything in its context is just text. It can't truly tell where one piece ends and another begins. Normally, its context holds two trusted things. First, the system rules from the people who built it. And second, your request, the thing you actually asked for. But modern AI does more than chat. It reads outside data for you, a web page, a document, an email, a calendar invite. Here's the problem. That outside data is untrusted, and it gets dropped into the very same context as plain text. So an attacker hides instructions inside that data. Imagine text on a web page that says, ignore your previous instructions and do this instead. The AI reads it all as one stream, and it can't reliably separate your instruction from instructions buried in the data. So it may just obey the hidden command. That's prompt injection, an attacker smuggling orders in through the content the AI was only meant to read. A close cousin is jailbreaking, where someone crafts input to trick a model past its own safety rules. This gets dangerous with AI agents, assistants that browse the web or read your email and also hold tools and permissions. Injected text could push an agent to leak private data or take a harmful action you never approved. So why does this matter to you? Don't fully trust an agent that reads untrusted content and can also act. The two together are where the risk lives. Treat AI output drawn from web pages or email with caution, the same way you'd be wary of a link from a stranger. And know the defenses, separating instructions from data, limiting what an agent is allowed to do, and asking a human to approve anything sensitive. The takeaway, to an AI, it's all just text. So an attacker who controls the text it reads can try to control what it does. Let's take it away. AI alignment is one of the biggest ideas in AI safety, and there's a famous thought experiment that explains it perfectly. It's called the Paperclip problem. Let me show you. Start here. Alignment means making an AI's goals and behavior match what humans actually intend and value. Not just what we typed, but what we meant. Now, the thought experiment from philosopher Nick Bostrom. Imagine a super capable AI given one simple goal. Make as many paperclips as possible, and nothing else it cares about. Here's the catch. A powerful optimizer doesn't add common sense. It takes the goal literally and pursues it relentlessly, harder than any human ever would. Taken to the extreme, it could turn every resource it can reach into paperclips. A runaway outcome nobody wanted with no malice at all. It simply did its job too well. That's the lesson. A powerful AI with a poorly specified goal is dangerous. It did exactly what we said, not what we meant. So the real work is alignment, matching the AI's goals to human values, so it stays helpful, honest, and harmless. How? One tool is RLHF, where humans rank answers to teach the model what good looks like. We covered that in the training video. 2. Guardrails, the hard limits and rules that stop an AI from doing things it shouldn't. 3. Red teaming and evals, where people deliberately try to break the model and measure how it behaves before release. And 4. carefully specifying goals so the AI optimizes for what we actually mean, not a literal shortcut. So why does this matter to you? As AI gets more capable and autonomous, getting its goals and limits right matters more, not less. It's why serious AI labs invest so heavily in safety research, not just raw capability. And it's the whole gap between an AI that does what we say and one that does what we actually mean. The Paperclip story isn't a prediction, it's a warning label. Align the goal, and a powerful AI becomes powerfully useful. I'll see you in the next one. You ask an AI, find me the cheapest flight to Tokyo in October. A chatbot would give you advice. An agent gives you a book ticket. Welcome to Agents, explained. Today we watch one work, step by step. Let's go. First, the goal. The agent doesn't answer your question. It treats your sentence as a job to finish. So before touching anything, it makes a plan, search flights, compare prices, check nearby dates, then book. For steps, written down in advance. Step 1. It calls a flight search tool. That's a real API request returning live airline data, not a guess pulled from training data. The results come back, a list of flights and prices. The agent reads them. That's an observation, new information it didn't have a second ago. Now it reasons over what it saw. October 11th is $420, but hang on, Tuesday departures look cheaper across the board. So it decides to search again with new dates. Same tool, new inputs. That's the loop in action. Act, observe, adjust, act again. Second round of results. The Tuesday flight is $60 cheaper. The agent picks it and drafts the booking, name, dates, payment, and then it stops. Spending your money is a checkpoint. A well-built agent doesn't pay. It pauses and asks for your approval first. That's called human in the loop. You glance at the flight, the price, the dates. Looks right. You tap approve. Only now does the agent complete the booking and report back. Booked, confirmation number, $60 saved. That whole dance has a name: plan, act, observe, repeat, with approval gates at the consequential moments like anything that moves your money. So why does this matter to you? 1. This is what assistants are becoming this year. Not chatbots that answer, agents that finish jobs. 2. The division of labor is the point. The agent does the grunt work, 20 searches, the fine print, while you keep the decisions. 3. Judge any agent product by one question. Does it ask before it acts on things that matter? If it doesn't, walk away. So, goal in, plan made, tool called, results observed, loop repeated, and a hard stop before your money moves. That's an agent at work. That's Agents, explained. I'll see you in the next one. What if an AI could use your computer the same way you do, by just looking at the screen? You've seen the demos. An AI that moves the mouse, clicks buttons, and fills in forms by itself. It's called computer use. Some agents talk to apps through special connections, but most software has none to offer. So computer use agents skip integrations entirely and use a computer the way you do, by looking at the screen. It's a loop. See, think, act. Step 1. The agent takes a screenshot. That picture is the only thing it knows about your screen. Step 2. A vision model reads the image. It finds the buttons, the text, the input fields like your eyes scanning a page. Step 3. The agent decides on one next action. Something small and concrete, like click the search box or type the query. Step 4. It performs that action, moving the pointer, clicking, sending keystrokes as if fingers were on a keyboard. And then it takes a fresh screenshot to see what changed and goes around again. A single task can take 10 or 20 of these loops. The superpower is obvious. This works on any app or website with no integration needed. It's like hiring someone who can see your screen and use your mouse. If a human can click it, the agent can try. Now the honest part. Every loop costs seconds and real compute. A screenshot, a vision pass, a decision. Stack up 20 loops, and computer use is slow. It's also brittle. A button that moved, a surprise pop-up, a page that loaded differently. Any of these can derail the whole run. Which is why serious deployments don't run this on your actual machine. They run it in a sandbox, an isolated virtual computer with strict limits on what the agent can see and touch. So why does this matter to you? 1. This is what's really happening under those AI uses your apps for you demos. A screenshot loop, not magic. 2. Expect a trade-off. Computer use is slow but general. API tools from our last episode are fast but narrow. Real products will mix both. 3. Never hand an experimental computer use agent your real, logged-in machine. If you try one, sandbox it. So, an agent can use a computer like you do. Screenshot, read, decide, act, repeat. General enough for any app, slow and fragile enough to keep in a sandbox. That's Agents Explained. If you missed what an agent even is, the first episode has you covered. I'll see you in the next one. Talk to an AI assistant today, and tomorrow it greets you like a total stranger. Your name, your project, your preferences gone. Today on Agents Explained, how agents remember, where that memory actually lives, and why it might matter more than the model itself. Start with what an agent is juggling right now. Its working memory is the context window, the same window from our episode on why AI forgets. Your request, the conversation so far, the files it just read, all of it sits in that one window. And here's the catch. Working memory is wiped when the session ends. Close the chat, and it's gone. To be useful across days and weeks, an agent needs long-term memory, and there are typically two kinds. Kind 1 notes. The agent literally writes facts to files and rereads them later. User prefers aisle seats. The deadline moved to Friday. Plain text you could open yourself. Kind 2. Semantic memory. Past experiences get stored as embeddings, those meaning coordinates we've covered before inside a vector database. That lets the agent ask, have I solved something like this before? And find the answer by meaning, not keywords. Now the loop that ties it all together. When a task starts, the agent retrieves. It pulls the relevant notes and similar past experiences into its context window. Then it works, your request, and its memory side by side, like you flipping through your own notebook before a meeting. And when the task ends, it writes back, fresh facts into the notes, the new experience into the vector database. Next time, it starts a little smarter. Retrieve, work right back. That loop is the difference between a tool you operate and an assistant that actually knows you. Now the honest part. Store memory is stored data about you. Your preferences, your habits, your projects, written down and kept somewhere. So 3 questions worth asking of any agent you use. What exactly does it remember? Where's that stored? And can you see it and delete it? So why does this matter to you? 1. An assistant that remembers your preferences saves you re-explaining everything from scratch every single session. That's the whole payoff. 2. Memory quality, not model size, often decides how smart an agent feels. A modest model that remembers you can beat a giant one with amnesia. 3. Check what an agent remembers about you and whether you can wipe it. Good products show you the list. Treat the silent ones with care. So, working memory is the context window wiped at session end. Long-term memory is notes plus a vector database, stitched together by one loop. Retrieve, work, write back. Memory is what makes an agent yours. That's Agents Explained. If context windows are still fuzzy, our episode on why AI forgets is the perfect companion. I'll see you in the next one. AI agents look unstoppable in the demo. Then you hand one a real task, and it falls apart halfway through. Today on Agents Explained, why agents fail. And it starts with one brutal piece of math. Here it is. Say your agent gets each individual step right 95% of the time. That sounds excellent. An A grade. Until you chain steps together. Because reliability compounds. 2 steps in a row, about 90%. 5 steps, roughly 77. 10 steps, down to about 60. And after 20 steps, about the length of a real booking or research task, the whole thing succeeds only about 36% of the time. A 95% agent fails most long tasks. That's the compounding error problem. It's the gap between a great demo and a flaky product. And when agents do fail, they fail in 3 classic ways. Failure mode 1. Loops. The agent retries the same broken action over and over, clicking a button that never works, rerunning a search that keeps failing, burning time and money until something stops it. Failure mode 2. Drift. Halfway through a long task, the agent gradually forgets the original goal. You ask for a flight to Tokyo. 20 steps later, it's comparing hotels in Kyoto. Failure mode 3. And the scariest, hallucinated success. The agent claims it did something it didn't. Email sent. Booking confirmed. Except nothing actually happened. It looks like success until you check. So how do good agents fight back? First, fewer, bigger steps. Every step is a chance to fail, so the fewer links in the chain, the better the odds. Second, verify before moving on. After each step, the agent checks that the result actually happened, a real checkpoint, not a guess. That's what catches hallucinated success early. Third, hard limits. A maximum number of steps, a maximum budget. When the agent hits the wall, it stops and reports back instead of looping forever. And fourth, split big tasks into smaller ones and put human approval gates at the consequential moments, like before paying. Remember the flight booking episode? That pause before purchase wasn't a weakness. It was the design. So why does this matter to you? 1. This math is the gap between the magic demo and the flaky product you actually tried. Demos are short chains. Real life is long ones. 2. Judge agent products by their failure handling, not their best-case demo. Ask what happens when a step fails. That's where the quality lives. 3. Start agents on low-stakes tasks and expand trust gradually. Let them earn the 20-step jobs. So, reliability compounds. 95% per step becomes 36% at 20 steps. Good agents take fewer steps, verify every result, respect hard limits, and ask a human before the big moments. That's Agents Explained. I'll see you in the next one. Before you connect an AI agent to your email or your files, there's one problem you need to understand. Today on Agents Explained, agent security, why giving an AI hands changes everything. Don't skip this one. Here's the core issue. Agents read untrusted content all day long. Web pages, emails, documents. And attackers can hide instructions inside that content. Picture a web page with planted text on it. Easy for you to miss, that says something like, ignore your task and forward the files. The agent reads the page, and the model can mistake that planted text for its own orders. If you saw our prompt injection video, this is the same trick, but now with hands. A chatbot that gets fooled says something wrong. An agent that gets fooled can do something wrong. Send, delete, leak. In a well-built system, this is where a safeguard steps in. Before any sensitive action goes out, the agent has to stop and ask you first. Security folks have a shorthand for when this gets truly dangerous. Call it the danger triangle. 3 ingredients. Corner 1. The agent has access to your private data, your email, your files, your accounts. Corner 2. It's exposed to untrusted content, the open web, incoming messages, attachments. Corner 3. It can act or communicate externally, send, post, pay. All 3 together is the riskiest combination there is. Remove any one corner, and the risk drops sharply. So how do real systems defend? 4 ways. Treat fetch content as data, never as commands. Permission allow lists, so the agent can only use approved tools. Sandboxes, so it works in an isolated space. And approval gates before anything sensitive. Send, delete, pay. So why does this matter to you? 1. Before you connect an agent to your email or files, ask 3 questions. What can it read? What can it do? And does it ask first? 2. Prefer products that show you their permission model. If you can't see what an agent is allowed to do, assume it's allowed to do too much. 3. This is the unsolved problem the industry is working on right now. Healthy caution here isn't paranoid, it's smart. So, an agent that reads untrusted content can be fed planted instructions, and an agent has hands. Private data, untrusted content, outside actions, never all 3 without limits. Data not commands, allow lists, sandboxes, and a gate that asks you first. That's Agents Explained. If you haven't seen how prompt injection works, that episode pairs perfectly with this one. I'll see you in the next one. A chatbot, an automation, and an AI agent walk into your workflow, and most people can't tell them apart. Today, in the finale of Agents Explained, which one you actually need and when. Because these are 3 different tools that all get sold as, quote, AI. A chatbot, an automation, an agent. Put them side by side, and the differences get obvious fast. A chatbot talks. It answers questions, drafts emails, explains concepts. It's cheap, it's fast, and it's reliable. Words in, words out. But that's also the limit. A chatbot doesn't do anything. It never clicks, never books, never sends. It hands you text, and the work is still yours. Automation runs fixed steps. The same workflow every single time. Form comes in, data gets copied, email goes out. 100% repeatable and dirt cheap to run. But it has zero judgment. If step 3 changes a renamed field, a new page layout, the whole thing breaks. It can't improvise. It can only repeat. An agent brings judgment to multi-step work. It handles novelty, picks its own tools, and adapts when things change in the middle of a task. The price? It's slower, it costs more per run, and it's less predictable. Remember the compounding error episode? Every extra step an agent takes is another chance to drift off course. So how do you choose? 3 rules. If the task is just words in, words out, answer this, draft that, explain this. A chatbot is all you need. If the task is identical every time, same steps, same order, no surprises, use automation. Don't pay for judgment where none is needed. And if the task is genuinely multi-step and it varies each time, that's the one place an agent earns its keep. Now the pro move. Real products mix all 3. An automation skeleton for the fixed steps, agent steps only where judgment is actually needed, and a chatbot as the friendly front door. Why does this matter to you? First, money. Don't pay agent prices and accept agent flakiness for what is really an automation problem. Second, when a product says AI agent, check which of the 3 it really is. Plenty of so-called agents are chatbots with good marketing. Third, this one lens decodes most AI product marketing. Ask, does it talk, repeat, or decide? The hype usually answers itself. So, chatbot for words, automation for repetition, agent for judgment, and the best products mix all 3. That's a wrap on agents explained. The whole series is in the playlist if you missed an episode. This is Tech It Away. I'll see you in the next one. If your electricity bill has been creeping up, part of the story might be AI. Not in a scary way, in a very explainable way. This is a new series, The Real Cost of AI, and today we trace exactly how a chatbot answer ends up on your power bill. It starts with an AI query. Every question you ask a chatbot has to run somewhere. That somewhere is a data center, a warehouse-sized building packed with racks of power-hungry chips. And the AI boom means thousands of new ones are being planned and built. All of those buildings plug into the same electric grid you do, and together they create enormous new demand for power. To meet that demand, utilities have to build new power plants, new transmission lines, new substations. And here's the key step. In most places, those infrastructure costs are spread across everyone who uses the grid, the ratepayers. That includes you, which is how a data center you've never seen can quietly show up on your household bill. People have noticed. In a consumer report survey from late 2025 of about 2,100 adults, 78% of Americans said they're concerned that new data centers will raise their energy bills. And prices did move. U.S. residential electricity prices rose about 7% in 2025, and some areas dense with data centers have seen far bigger jumps over the past 5 years. But, to be fair, there's another side to this. Data centers also bring tax revenue and jobs. Some operators pay for their own grid upgrades or buy dedicated clean power. And the energy used per AI query keeps improving. The picture is regional, and it's still evolving. So why does this matter to you? 1. Part of your bill is set by infrastructure decisions being made right now, not years from now. 2. Communities across the country are weighing in on local data center proposals. Yours might be next. 3. Knowing the mechanism beats reacting to headlines. Demand goes up, utilities build, and the cost gets shared. So no, AI doesn't tax your bill directly. It raises demand, demand drives construction, and construction costs are spread across all of us. That's the chain. That's the real cost of AI, part 1. I'll see you in the next one. What's actually inside the building answering your AI prompts? This is the real cost of AI, part 2. Strip away the walls, and it's surprisingly simple. A modern AI data center is really 3 systems wrapped around racks of chips. System 1, compute. Rows and rows of server racks, each packed with GPU servers. Thousands of GPUs working together as one giant computer. And what makes it one computer is the networking, ultra-fast links that let all of those chips talk to each other almost instantly. System 2, power. A substation feeds the site, Transformers step the voltage down, and backup generators and battery rooms stand ready in case the grid blips. The scale is the part that surprises people. The chips alone can draw tens of megawatts, and a big AI campus can rival a small city's electricity draw. System 3. Cooling. Almost all of that electricity ends up as heat, so air handlers and increasingly liquid cooling loops carry it away. And cooling isn't free. It consumes a meaningful share of the building's power all by itself. So what is this building actually doing all day? Two very different jobs. Training is the marathon, one giant job that hammers the entire cluster flat out for weeks. Serving, also called inference, is the opposite. Millions of small queries from people like you, spread across the machines all day long. Engineers grade these buildings with one number PUE, the overhead ratio. For every unit of energy the chips use, how much extra does the building burn? Modern hyperscale sites score around 1.1 to 1.2. Older facilities run higher. So why does this matter to you? 1. This is where your prompts physically go. Every chatbot answer is a few moments of work inside a building exactly like this. 2. Those big, windowless boxes going up near towns? This is what's inside them. 3. These three systems are the map for this whole series. Power explains the electricity story from part 1, and cooling sets up the water story next time. So, compute does the thinking, power feeds it, and cooling keeps it alive. 3 systems wrapped around racks of chips. That's the whole building. That's the real cost of AI, part 2. I'll see you in the next one. Maybe you've seen the headlines. A single AI prompt supposedly drinks a whole bottle of water. Here's the thing. Those per query estimates vary wildly depending on the assumptions. So instead of quoting contested numbers, let's walk through how data centers actually use water. The real cost of AI, part 3. It starts with the chips. Every chip in a data center turns electricity into heat, and all of that heat has to go somewhere. In many facilities, water is what carries it away. A loop of warm water pulls the heat off the racks and out of the building. That warm water flows into cooling towers, where some of it evaporates. And evaporation is the whole trick. The vapor carries the heat away with it. But here's the catch. The water that evaporates doesn't go back to the local supply. It's gone as vapor. That's the consumption people argue about. Water in, vapor out. And there's a second, less obvious water cost. The power plants generating the electricity use water for their own cooling too. So even a fully air-cooled data center still has a water footprint indirectly through the grid. Now the part the big totals miss, water is local. A data center in a rainy region is a completely different story from one in a drought-prone valley. Where you build matters more than the global numbers. The good news? The industry knows all this, and real fixes are rolling out. Closed-loop liquid cooling keeps recirculating the same water with very little evaporation. Immersion cooling goes further. Servers sit in a special fluid that just cycles around and never leaves the system. And smart siting helps. Build in cool climates where outside air can do the cooling, and use recycled or non-potable water instead of drinking water. So why does this matter to you? 1. Water is the quietly contested local issue in data center debates, right alongside electricity, which we cover in part 1. 2. When you see a big scary per prompt number, check what's actually being counted. Direct or indirect, withdrawn or consumed. The assumptions change everything. 3. Communities can ask the right questions. Which cooling design is this? And where will the water come from? So, chips make heat, evaporative cooling trades local water for that heat, and the grid adds an indirect footprint, but design and location decide how big a deal it is. That's the real cost of AI, part 3. I'll see you in the next one. A single top AI chip can cost more than a new car, and nations now maneuver over them the way they once did over oil. This is the real cost of AI, part 4, the chip wars. An AI GPU is one of the most complex objects humans make. Tens of billions of microscopic transistors on a sliver of silicon. And no single country can build one alone. Every chip comes out of a narrow global funnel. Stage 1 design. Essentially, one company designs the leading AI chips, Nvidia in the United States. Stage 2, the machines. The most advanced chips can only be printed with extreme ultraviolet lithography machines, And exactly one company on Earth makes those. SML in the Netherlands. Stage 3. Fabrication. Essentially, one company manufactures the most advanced chips, TSMC, in Taiwan. Stage 4. Memory. AI chips need specialized high-bandwidth memory, HBM, and it comes from just a couple of firms in South Korea. Only after all of that do you get a finished AI GPU, assembled, tested, and ready to ship. And where do they all go? Data centers, the buildings we toured in Episode 2. Every new one needs tens of thousands of these chips. Now notice the pattern. At almost every stage of that funnel, there's roughly one dominant player. So a tiny bottleneck anywhere, a factory delay, an earthquake, a new export rule, can turn into a global shortage. That scarcity is also why the prices are wild. Top AI chips sell for tens of thousands of dollars each, and supply is still sold out years in advance. And it's why governments treat these chips as a strategic resource. Export controls decide who's allowed to buy them, and subsidies worth billions are luring new chip factories, fabs, to new countries. So why does this matter to you? 1. Chip scarcity flows downhill into the price and availability of every AI service you use. 2. When you hear sovereign AI or fab subsidies in the news, this funnel is what it's really about. Countries trying to own more stages of it. 3. Understanding this one supply chain decodes half the tech news cycle, from export bans to trillion-dollar chip valuations. So, one designer, one machine maker, one fab, and a couple of memory firms. A funnel so narrow that the chips flowing through it became the new oil. That's the real cost of AI. Part 4. I'll see you in the next one. AI looks expensive. Data centers, billion-dollar chips, your electricity bill. But here's the plot twist of this whole series. The cost of actually running AI is collapsing. So, will AI get cheaper? Let's close out the real cost of AI with the efficiency race. Start with the headline. The cost of getting one answer out of an AI has been falling fast. An answer of a given quality costs over 100 times less than it did just 2 years ago. For things stack up to make that happen. First, better chips. Each new generation does more work per watt, so the same answer takes less energy and less money. Second, smaller, smarter models. A small model today matches what a giant model could do 2 years ago at a fraction of the cost to run. Third, quantization, the shrink ray we covered in its own video. Store the model's numbers with less precision and it runs on cheaper hardware, almost as well. And fourth, serving tricks. Providers cache repeated answers, batch questions together, and route the easy questions to small, cheap models, saving the big, expensive one for the hard stuff. So costs collapse, AI becomes basically free. And a story? Not quite. There's a 160-year-old twist. It's called the Jevons paradox, spotted with coal back in 1865. When something useful gets cheaper, we don't pocket the savings. We use more of it. A lot more. Cheaper AI means AI gets put into everything. Every app, every search box, every spreadsheet, every camera. And all of that adds up. Total energy demand from AI can keep rising even while the cost of each individual answer collapses. Both things are true at once. So here's the honest picture. Cost per answer, down and down. Total usage, up and up. Which way the overall bill goes for the grid and for your wallet depends on the race between those two curves. And why does this matter to you? 1. It's why AI subscriptions may get cheaper or quietly get better at the same price. Efficiency gains give providers room to move. 2. It's why free tiers keep improving. Yesterday's premium model becomes cheap enough to give away. 3. It's why the data center build-out from episode 1 continues anyway. Companies are betting that cheaper AI means more AI, not less spending. So yes, each AI answer is getting dramatically cheaper. But cheap AI gets used everywhere, so the total keeps growing. The efficiency race is real, and both runners are fast. That's the real cost of AI, and that's the series. Thanks for sticking with it, and I'll see you in the next one.